Hey everyone, so today we are going to talk about coordinate vector, one of the very important concept in linear algebra. So we will see the definition, we will see the concept, then we will see that why talking about this makes sense. That means, is this concept a well defined concept? And I will support my argument by giving you a very nice theorem. Okay, and after that we will see some very nice examples which will help you to understand this concept overall. Okay, so what is a coordinate vector? So once you have a vector space, so if you assume that your V is a vector space over some field F, okay, F is some field. If you don't know what do you mean by a field, then you can consider real numbers. Okay, so suppose your V is a vector space over real numbers, and you consider your V as a basis V1, V2 up to Vn. So this is a basis subset of my vector space V. Basis as in what? This set is a linearly independent set, and when you take the span of B means what? Spanning set of B means what? You take all possible linear combination. Okay, so when you take all possible linear combination, you get the complete vector space V. So you have B as a set. Okay, now what you do is you take a vector in the vector space V. But since B is a basis, I know that my V is nothing but it's a span of a basis set B. That means what? How my V bar will look like? It will be some linear combination of the basis vectors. That means some C1 V1 plus C2 V2 plus Cn Vn by the definition of span. For some Ci belongs to my field F, or for some Ci's belongs to my real number. Okay, they are some scalars. You define coordinate vector of V, this is the square bracket notation, with respect to the basis B. My B is an ordered basis. So once you fix a basis, that means this ordering is fixed. What do you mean by ordered basis? I had talked in my earlier lecture. You can have a look, link you can find in the description. So you have an ordered basis. So coordinate vector of V with respect to B is defined as a column vector. Okay, it is nothing but a column vector. What is n? It is a dimension of V. N cross 1. And what are the column entries? They are nothing but the scalars C1, C2 up to Cn. So this is how you define a coordinate vector. Okay, so it's very simple idea. You have a vector space, you take a vector in that vector space. Now you know that vector V can be written as the linear combination of basis vector. Why? Because since it's a basis, its span will be the complete vector space. So your V bar is in the span, that means V bar will look like this. So you have C1 to Cn. Write them as a column wise, that is what your coordinate vector is. Okay, so we defined the coordinate vector. Now one can ask, is this make sense? That means I am writing V bar as C1 V1 plus C2 V2 plus Cn Vn. On the other hand, suppose you are writing V bar, you are writing the same vector V bar as D1 V1 plus Dn Vn. So in that case, what will be your coordinate vector? In that case, your coordinate vector will be D1 to Dn. But then this should not happen, right? If I am working on a problem and if I am playing with this coordinate vector, you are also playing with the problem and you are playing with this coordinate vector, then things are different, right? It should not happen. That means this concept is not well defined. If my Ci's are different than Di's, then this is not a well defined concept. That means what I want to say is, we will see that there is a very nice theorem that once you take a vector, you know that because of the spanning thing, you can write it as a linear combination of basis vector. And now we are going to use the linear independent thing to prove that a vector V has a unique representation. Once you take a vector V and you write it as a linear combination of basis vector, then this is a unique combination. You cannot have any other combination. Okay, so if I am writing V bar as a combination of basis vector, and if you are also writing a vector V as a combination of basis vector, then both that combinations has to be same. That means my Ci's has to be equal to Di's. Okay, so this combination is a unique combination, and therefore anyone in the world, if he or she will take the vector V and if he tries to write down as a linear combination of basis vector, then we all will get the same coordinate vector. Okay, so that's the beauty of this concept, and therefore this is a well defined concept. And now let me try to prove this. So suppose if V bar can be written as C1 V1 plus C2 V2 plus Cn Vn, and suppose your V bar is also written as D1 V1 plus D2 V2 plus Dn Vn. If I subtract these two equations, V bar minus V bar is 0 bar. This is C1 minus D1 into V bar. Let me write it down. C1 minus D1 into V1 bar plus C2 minus D2 into V2 bar plus Cn minus Dn into Vn bar. So I am having a linear combination of V1 V2 up to Vn equal to 0. But what are V1 V2 up to Vn? They are the basis vector, and that means they are linearly independent. So if the linear combination is 0, that means what? All my scalars has to be 0. That means all my Ci's are equal to Di for I equal to 1 to n. So once you take a vector and you write it in a linear combination of basis vector, then that is a unique combination. Okay, and therefore once you have the basis V, okay, once you have a vector space V and the ordered basis V, the order is fixed, then this is a well defined concept. Okay, everyone will get the same coordinate vector. Okay, so we have seen the concept. Now let's try to see some examples so that this will be much more clear. So let me take the first example, the simplest example. So R3 is my vector space over real numbers. My B is the one basis, standard basis E1, E2, E3. B prime is another basis, which is E2, E3 and E1. As I said, B and B prime are same, but as an ordered set they are different. Okay, because I have changed the order. So as an ordered set they are different set. Let me take V bar 5, 6, 7 in R3. Now this 5, 6, 7 I can write as 5 times the first vector plus 6 times the second vector plus 7 times the third vector. So what is the coordinate vector of V with respect to the basis B? It is nothing but you write down the coefficients, which is 5, 6, 7. For the standard basis, the vector and the coordinate vector are always same in that order. But if I want to write V bar as a linear combination of vectors in B prime, so this will be what? Here it is 6. So it is 6 times the first vector 0, 1, 0 plus 7 times the second vector plus 5 times the third vector. So the coordinate vector of V with respect to B prime is nothing but 6, 7, 5. And that's why I was stressing on the point that the order is important. Once you change the order, the coordinate vector will change. Okay, so whenever you want to find the coordinate vector, you have a vector space and you fix the order of the basis, and then you start finding the coordinate vector. Okay, so this was the one simple example. Let's go for another example. So consider the vector space V as all 2 cross 2 matrices over real number. So since this is 2 cross 2 matrices, I know the dimension is 4, therefore the basis will have 4 elements. So let this be the basis for V. If you are not sure, then make sure you first prove that B forms a basis. And if you are getting stuck, you can ask me in the comment section. So you have to first prove B is a basis, but as if now I will assume that this is a basis. Now you take V bar as 7, 8, 17, 19, which is an element of V, and I want to write this as some multiple of the basis vector. So something into the first one plus something into the second basis vector plus something into the third basis vector and something into the last basis vector. So this will be C1, C2, C3, C4. Now you can see the last component is 0 and here it is 1. So your C4 has to be 19. For C3, the third component, C3, this is 0, this is 0. So you have C3 plus 19 is equal to 17. So 19 plus something should be 17. So C3 has to be minus 2. Now here you have 8. You have C2 minus 2 plus 19. So C2 plus 17 is 8. So C2 plus 17 is 8. That means C2 has to be 7, 8, 9. Right, it should be minus 9. And one can check. Minus 9 minus 2 is minus 11. Minus 11 plus 19 is 8. And what will be here then? You have 8 over here and you want 7. So it should be 1. Because 9 minus 2 is, so minus 9 minus 2 is minus 11. Minus 11 plus 19 is 8. 8 minus 1 is 7. So therefore, for this vector, with respect to this order basis, my coordinate vector is minus 1, minus 9, minus 2 and 19. If you feel my calculations are incorrect, you can correct me in the comment section, not a problem. But I hope you got the idea. Okay, if you are not able to figure it out, what is C1, C2, C3, C4, you simply multiply inside C1 0 0 0, C2 C2 0 0, C3 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 0, C4 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 C4. Then you add them, you equate both the matrices, you will have 4 equations in 4 unknowns, and you try to find C1, C2, C3, C4 by elimination method or by row operations, whichever you like. So that's how one should find the coordinate vector. Now let me give you one homework problem. So here are the 2 homework problems for you. First one is P3R, all polynomials of degree at most 3. So we know that the dimension is 4. So let me take this as the basis. Make sure you are comfortable with the order x cube 1 x square x. Now write down v bar as a combination of this and tell me the order coordinate vector for this vector with respect to this basis. Second is set of all 2 cross 2 symmetric matrices. And one of the basis set is this 2 0 0 0, 0 1 1 0 and 0 0 0 7. Okay, this is a 3-dimensional space. And let v bar be 4 6 6 8. This is a symmetric matrix. You write v bar as a combination of b and tell me what is the coordinate vector. And you have to comment both the answers in the comment section. And if you have any other doubt, then that also you can ask me in the comment section. And if everything is clear, then do not forget to like, share and subscribe. Thank you.